Hi everyone, today we are going to learn about impulse. So impulse is just a change in momentum, right? When you stop, when you start up again, if you're in a car, any kind of movement involves a change in momentum. And so the change in momentum is represented with a J. It's kind of like the weird one, just like momentum is the P. Impulse is represented by a J. But most of the time, I'll probably be using this delta P. Remember, delta just means change in, okay? And we know that a change in momentum usually means a change in velocity. Okay, usually an object does not change its mass. I'm not saying that it can't, but in most of the cases that we're going to solve, right, we're really going to solve it as m Vf minus m Vi, or I like to solve it as m and then Vf minus Vi. Okay, notice m is in both of those equations, and so I can combine them together. Also, just remember then that m delta V is equal to V delta T, right? That's our other formula for impulse, is force times time. Also remember, we went through this, I think, in the last notes, but that F is inversely proportional to T. If we increase the time, right, if we increase, I'm just going to write with my highlighter, then we decrease the force. Okay, those are inversely related. And we can see that with these two illustrations here, right? Here is a moving truck stopped by some hay, and then a moving truck stopped by a wall. Notice both of those actually end up, right? They start with the same velocity, they end with the same velocity, right? This is my velocity, right? Let's pretend that this is 50 kilogram truck, and it's moving at 50 meters per second. Then it goes to, right, 50 kilograms to 0 meters per second. And really, right, if this is VF, right, I'm just going to use this guy here to be VF. That means this is VI. Okay, and we can see that the change in momentum is 2,500. It's actually probably a negative 2,500 kilogram meters per second, right? Because it's actually the opposite of the direction, right? My velocity ends up being negative, and so I get a negative momentum, which, remember, just means that it's opposite the direction. This is the same here on the right side picture. We know that it starts at 50 kilograms at 50 meters per second. This is VI, right? And then we know that it ends at 50 kilograms and 50 meters per second. Oh, sorry, not 50. 0 meters per second, stopped by the wall. And this is VF. And so my momentum change, right, is the same, a negative 2,500 kilogram meters per second. And that's what it says here. It says that the impulse, which is the change in momentum, is the same for both scenarios. But because the time it takes, right, for the haystack versus the wall is greater, that means my force, right, is smaller in the haystack versus with the wall. Okay, that's sort of the application of impulse, is that if you can increase the time, you can decrease the force. This is what saves lives with airbags, right? Think about trampolines, think about when you fall, you want to make sure that that fall time takes actually kind of a longer time. That's why you kind of roll, in a sense, instead of just landing on your feet and impacting, or like landing on your shoulder, right? Because that can break your bone. But if you can roll, right, you might get a bruise, but you won't actually break a bone. Okay, example 1. the concept. A boxer moving his head away, that's really important, right? Moving away from the glove versus moving toward the glove, okay? Again, you can see in the picture, right, that this time is big versus this time being small. Therefore, remember, force and time are inversely related, right? So as the time increases, the force applied decreases. Right? And so you would rather be hit moving away than kind of moving toward. The force of that impact is greater. Remember, momentum stays the same, or the change in momentum stays the same, but that force changes. Example 2, these are our relationships. So if we use this formula here, right, J equals F times T, we can see that, remember, if my J is equal to F times delta T, and it says that the time remains the same, so I'm going to go ahead and take that out of the equation, and what we see is J is proportional to F. Remember, they're on opposite sides of the equation, so doubling the force, this is a direct relationship. So doubling the force will double the impulse. Okay, they're direct because they are opposite sides of the equation. If the force remains the same, so J equals F delta T, so now we're taking force out of the equation. What we see is J, impulse, is proportional to the change in time. So if we triple the time, again, those are on opposite sides of the proportionality, right? This is a direct relationship, so it will triple the impulse. Okay. The last one, right, what we see is if time is cut in half and the impulse remains the same. So notice F delta T, these guys are now on the same side of the equation. So if we would solve and set those sort of proportional to each other, it would end up being F is proportional to 1 over T. This is an inverse relationship because they are on the same side of the equation, multiplied by each other. So if the time is cut in half, that means my opposite happens and the force will double. Okay, make sure you know those proportionalities, how those variables are related to each other. We don't have to do example 3, A or B. It's kind of all the same. I do want to talk about C, and it's all the same, right? How does this theorem explain why when you jump up, you should bend your knees when you land? It's the same thing, right? Increasing the time of impact decreases the force. In layman's term, right, kind of what we talk about, right, and what people talk about is like it absorbs, right, the impact. It's not actually true, right? But that's what like shock absorbers are, right? Is that it's increasing the time for your car to go over the bump or feel that force, and so it decreases that force so you don't feel it quite as much in your car, right? Last example, there's a rubber ball and a clay ball, both with a mass. I'm going to go ahead and put the mass in red, right? Thrown at a velocity. So this is my initial velocity of 10 meters per second, right? This is VI, and this is M here. Okay, the clay ball hits the wall and immediately comes to rest. This is VF, then sticks to the wall. Find the change in momentum. Okay, well, if I do change in momentum, I have a mass and 2 velocities, so that's what I'm going to use. That formula is M, right? VF minus VI, right? There we go. Then we put our numbers in. My mass is 1 kilogram. Then I multiply by VF, which is 0 meters per second, minus my VI is 10 meters per second. Remember, this 0, right, kind of basically doesn't count. And so what we can see is it's 1 kilogram times negative 10 meters per second. This is a negative 10 kilogram meters over seconds. That's my impulse. Okay. Then it says, instead, the ball hits the wall, but it takes 0.5, so half a second to come to rest. What was the average force on the ball? So again, I'm using my other equation now, right? Not the m change in velocity. I'm now going to use the force times the change in time. Oh, I can use colors for those guys too. Let me do that, right? My force can be in pink. And my time, right, this is t, right, can be in orange, okay? So then I actually know from above that this is negative 10 kilogram meters per second is equal to my force is what I don't know, right, because it's asking what's the average force. But my time is 0.5 seconds. In order to solve this equation, I go ahead and divide both sides by 0.5 seconds, and I end up with a force of negative 20. Remember, force is in newtons, 20 newtons. Okay, how does extending the time of the collision change the force? Remember, increased time decreased force. Okay. C, now the ball hits the wall, but it bounces back at negative 5 meters, bounces back at 5 meters per second. So this is my new VF, right, is 5 meters per second, but notice it says it bounces back. So remember, this VF will be negative, VF will be negative because it's opposite direction. Okay, what's the change in momentum? So here we go. Change in momentum is my mass times my VF minus my VI. And so I can go ahead and write my mass in, which is 1 kilogram. My VF now, remember, because it's in the opposite direction, I'm putting a negative in front of the 5 meters per second. Then I'm subtracting my VI, which is positive 10 meters per second. And so that ends up being a negative 15. So my change in momentum is negative 15 kilogram meters per second. Okay, and what I can see, right, notice the next thing is, how does bouncing change the impulse? If we look at this one here, right, I'm going to go ahead and, highlight it in blue, right? Negative 15 compared to negative 10, right? A bounce increases the change in momentum. Oops, let's try that again. In momentum. There we go.